Alright, let's talk about arrays. Probably the most used data structure. This is part 1 of 2 in the array videos. The reason the array is used so much is because it forms a fundamental building block for all other data structures. So we end up seeing it everywhere. With arrays and pointers alone, I'm pretty sure we can construct just about any data structure. So an outline for today's video. First, we're going to begin by having a discussion about arrays and answer some fundamental questions such as what, where, and how are arrays used. Next, I will explain the basic structure of an array and the common operations we are able to perform on them. Lastly, we will go over some complexity analysis and look at some source code on how to construct a dynamic array using only static arrays. Discussion and examples. So what is a static array? So a static array is a fixed length container containing n elements which are indexable, usually on the range of 0 inclusive to n minus 1 also inclusive. So a follow-up question is, well, what is meant by being indexable? So answer to this means that each slot or index in the array can be referenced with a number. Furthermore, I would like to add that static arrays are given as contiguous chunks of memory, meaning that your chunk of memory doesn't look like a piece of Swiss cheese with a bunch of holes and gaps. It's contiguous. All the addresses are adjacent in your static array. Okay, so when and where is a static array used? Well, they're used everywhere, absolutely everywhere. It's hard to make a program that doesn't use them, in fact. Here are a few places you may or may not know that do use arrays. So, of course, the first simple example is to temporarily store objects. This is the most common use of arrays that you are probably familiar with. Next is that we use arrays as buffers to store information from an input or an output stream. Suppose you have a really large file, for instance, that you need to process, but that file is so big it doesn't fit in all in memory. So we use a buffer to read small chunks of the file into the buffer or the array one at a time, and so eventually we're able to read the entire file. I also like to use arrays as lookup tables because of their indexing property. So this is a really easy way to retrieve data from a lookup table if you know where everything is and it's supposed to be and at what offset. Next, we can also use arrays as a workaround in a programming language that only allows one return value. So the hack we use then is to return a pointer or a reference to an array which then contains all the return values that we want. This last example is a bit more advanced, but arrays are heavily used in a programming technique called dynamic programming, with tabulation to cache already computed subproblems. So a classic example of this might be the knapsack problem or the coin change problem. Alright, time to talk about some complexity. So the access time for a static array and a dynamic array is constant because of the property that arrays are indexable. So searching, however, can take up to linear time because we potentially have to traverse all the elements in the array in the worst case, such as if the element you're looking for does not exist. Inserting, appending, and deletion from a static array doesn't really make sense. The static array is a fixed size container. It cannot grow larger or smaller. When inserting with a dynamic array, this operation can cost up to linear time because you potentially have to shift all the elements to the right and recopy all the elements into the new static array. This is assuming we're implementing a dynamic array using static arrays, however. Appending, though, is constant. Doesn't that seem a little strange? Well, when we append elements to a dynamic array, we have to resize the internal static array containing all those elements. But this happens so rarely that appending becomes constant time. Deletions are linear for the same reasons that insertions are linear. You have to shift all the elements over and potentially recopy everything into your static array. Okay, so we have a static array A I've defined at the top. So A contains the values 44, 12, -5, 17, 6, 0, 3, 9, 100. Currently all the elements are distinct, but this is not a requirement of an array. Also remark that the very first element, 44, has index or position 0 in the array. Not 1. This confuses many intro computer science students who have no idea. The confusing part is that most, if not all, of mathematics is 1-based, while computer science is 1. Now, if we look at A, you can see that it contains the values 44, 12, -5, 17, 6, 0, 3, 9, and 100. Currently, all the elements are distinct. However, this is not at all a requirement of the array. Also remark that the very first element, 44, is indexed or positioned at index of 0 in the array. Not 1, 0. This confuses a lot of intro computer science students. The confusing part is that most, if not all, of mathematics is 1-based, while computer science is 0-based. This is what causes the confusion. But worst of all is quantum computing. I did research one summer in quantum computing during my undergrad, and the field is a mess. It tries to please mathematicians, computer scientists, and physicists all at the same time. And indexing just doesn't work well. Anyways, back to arrays. I should also note that the elements can be iterated over using a for each loop, something that's offered in some programming languages. It doesn't require you to explicitly reference the indices of your array, although the indexing is done internally, behind the scenes. The notation of the square brackets denotes indexing. So array A, square bracket 0, close square bracket is equal to 44, meaning A at position 0 is equal to the value 44. Similarly, A at position 1 is 12, A at 4 is 6, A at 7 is 9. But A at index 9 is out of bounds, and our program will throw an exception. Unless you're in C, it doesn't always throw an exception, unfortunately. Okay, now if we assign position 0 to be -1, that happens. If we assign index 5 to be 18, and if we assign index 6 to be 25. Let's look at operations on dynamic arrays. So dynamic arrays can grow and shrink in size as needed. So the dynamic array can do all similar get, set operations static arrays can do, but unlike the static array, it grows in size dynamically as needed. So if we have A containing 34 and 4, then if we add -7, it gets appended to the end. If we add 34 again, then it'll add it to the end. And we can also remove elements. So you see here our dynamic array shrank in size. Pretty cool, eh? Okay, so we already talked about this a little bit, but how do we formally implement a dynamic array? Well, the answer is typically this is done with a static array. But this is not the only way, of course. So first we create a static array with some initial capacity, usually non-zero. So as we add elements to the underlying static array, keeping track of the number of elements added. Once we have to add an element which exceeds the capacity of our internal static array, what we can do is we can double the size, copy all the elements into this new static array, and add the new element we need to add. Let's see an example. So suppose we create a dynamic array with an initial capacity of 2. Then we begin adding elements to it. So the little circle with the slash through it is a placeholder for an empty position. Okay, so we add 7, everything's fine. We add 9, everything's fine. But once we add 3, it doesn't fit in our internal static array, so we double the size of the array, copy all the elements in, and now we can add 3. Now if we add 12, everything's still okay, we're doing good. And if we add 5, okay, we have to do a resize again, so double the size of the container, copy all the old elements into this new larger array, and then finish off by adding 5. And similarly, we can add 6 without any issues. Okay, so I will be showing you an implementation of a dynamic array in the next video. If you're interested in the source code, it can be found at the link below. The link should also be provided in the description. So guys, thanks for watching, and hopefully I will catch you in the next video.